Now let us review that query, that how do we choose the group for reduction. Okay. To do that, in theory, we need to define a couple of terms: implicant, prime implicant, essential prime implicant. An implicant is any product term of an SOP for expression, any product term. Okay. A prime implicant is a product term which cannot be covered by any other more general or reduced term, means term with fewer literals. Okay. So as we have seen, like if we group mean term of 2, we get usually I would say for a 4 variable function, we usually get like 2 terms there, right? If it is an or 3 terms, basically 3 terms, and group of 4 we get 2 terms, and group of 8 we get 1 term, something like that. So we are kind of reducing the terms as we increasing the groups. Okay. So what is a prime implicant is that product term which cannot be covered by any other more general terms. So in terms of our previous examples, let's say we group, initially we grouped M1, M5, right? There because they're neighbor. Now, are they implicant? Yes, they are implicant. Like by grouping them, we came up with W bar, Y bar, Z, that's an implicant. But is it a prime implicant? No, because in this problem scope where we have this function, let's say this function had W, X, Y, Z as sigma. How do I make a sigma? Okay, doesn't matter. S for sigma. Okay, M 1 5 1 3 5 7. That's the function definition. Sigma of 1 3 5 7. So in this term, we can group 1 and 5 and 3 and 7, but they are implicant. In fact, M1, M3, M5, M7 individually they are implicant too. A prime implicant is your bigger group, the most biggest group you can make in the neighborhood. So in this case, we can make neighborhood of M1, M3, M5, M7 together because they are neighbor with each other. So that become my prime implicant. My prime implicant term is W bar Z, or sometimes we kind of represent as an SOP formulation. This is my sigma M3, and which is also my prime implicant. Now, what it mean in the slide, that which cannot be reduced to any fewer literals, means this. Like we can make a group of M1 and 5 which gives this. We can make group of M3 and 7 which gives this, but they are not the prime implicant, because we can further reduce these terms by combining 2 or more neighbors with them, right? So in this case, you see we combined them, we came up with W bar Z, and we cannot combine any other min term to further reduce this W bar Z. So that's why it is defined as a prime implicant. Now, essential prime implicant is a prime implicant. So it starts with a prime implicant. So it's a maximal group which covers output function in such a way, that no other combination of prime implicant can cover. So it covers at least one which is not covered by any other prime implicant. That's the definition of essential prime implicant. In our example, going back to this one, we don't have any other implicant or prime implicant at all. So this one is going to be my essential prime implicant as well, and what's reduced term is W bar Z. So with that, let's take another example. Okay. So we claim that, well, I have this FWXYZ with this, that will ultimately become your W bar Z XZ bar and something else. So let's see it. So we have 1357 group in this case, and we have this 4, 6, 12, 14. They are also group. How about this group, the red one, 4, 5, 7, 6? So what happens if you look at this green group? Let's take example of this green group 1357. This group is covering the term 1 and 3, which is not covered by any other group, right? But 5, 7 is covered by this red group. All right, that's okay. Now for the group of 4, 6, 12, 14, the mean term 12 and 14 are not covered by any other group, but mean term 4 and 6 are covered by this red group. That's okay. So that's why your group of 1, 3, 5, 7 is an essential prime implicant, and 4, 6, 12, 14 is essential prime implicant. By the way, why it is the implicant prime implicant in the first place? Because we cannot make any further bigger group from this group of 1, 3, 5, 7, for example. Now this one, red group, is not it's not an essential prime implicant. Why? Because if you see each of this mean term in this group, which is 4, 5, 7, 6, they are also part of some other prime implicant group, all of them. Okay, so this red group is not covering any such any such mean term or any such one visually, which is not covered by any other group. So that's why this is a non-essential prime implicant. So even if I write that term, like let's see, this red group's literal term would be W bar X, right? W bar X. We can readily drop it with the consensus theorem. W bar going with Z and X is going with Z bar, then we are pairing W bar X. By consensus theorem, we can just drop it, and we practically came up with the expression, which would be essentially a combination of these green groups, which are essential prime implicants. So that's the concept of essential prime implicant. The next slide is basically to show you that there can be some situations where there is no clear winner. A clear winner means like you cannot say that okay, this prime implicant is really my essential prime implicant or not. So this example is one such. Like we group everything, like make a max group of these given function, except for this box 15. Right now we are under question that what should be the group. So I can group this way, 13, 15, right, or 15, 11. Right? No matter what, like this is a valid group. This is a valid group. So both of them, 13, 15 and 15, 11, are my prime implicant. Now, if both are my prime implicant, which one is my essential prime implicant? Right? So we can write down taking 13, 15 as my essential prime implicant, or we can write down with the group 15, 11 as my essential prime implicant, and essentially both these reductions are good. Basically, they are the most reduced form from this K-map. So in my class, what I assume that first of all, I need to select one of them as my essential prime implicant, either 13, 15 or 15, 11. Because I must produce a term which covers this box 15, right? So in Google or any other theories, Boolean algebra, they basically say, okay, these red and blue groups are not essential prime implicant, just prime implicant. We are just picking up one. In my class, in this class, what we define them as essential prime implicant by choice. Okay, so we have potentially two candidates, 1315 and 1511, and by choice, we are making one of these group as essential prime implicant. This means we are making other group as non-essential prime implicant. Both are prime implicant. All of them are prime implicant. In fact, all these groups we made so far, all the green groups and this red and blue groups, they are prime implicant. And all the green groups are essential prime implicant because there is no ambiguity as such. Now between this group red and blue groups, we need to choose one of them as my essential prime implicant because I need to cover this box 15. Okay, I need to cover that mean term. So that's why by choice we are either declaring group of 13, 15 as my essential prime implicant, or we are declaring group of 15, 11 as my essential prime implicant and going forward with the reduction process. Another selection rule states that select the non-overlapping essential prime implicant as much as possible. What does it mean? So in previous example, we saw that like lot of overlap between prime implicant group, and we'll have many choices in problem like this one. Okay, a function is sigma m of 0, 1, 2, 4, 5, 10, 11, 13, 15, and we have this choice, right? One such essential prime implicant choice would be this. I'm not showing all the possible prime implicant group. Okay, another choice could be this one. Okay, so these are all, if you superpose this set, they becomes the set of all possible prime implicant. Okay, so I'm just showing the essential prime implicant based on what we can derive the reduced expression. So this is one such group. We can make this group. Also there is a possibility we can make this kind of group, right? So we have three different choices. This one, or this one, or a grouping like this one. This is a valid grouping, right? We pick up, we make all the possible prime implicants, then we choose the group which can ultimately cover the whole of the ones in the boxes. But the last one is not kind of desirable. Why? If you see, the last one has a grouping, number of group is 1, 2, 3, 4, 5 term expression, whereas the previous one, all of them has 1, 2, 3, 4 terms and 4 terms, right? So by choice of the group, even it appears that, well, I am choosing my group and it is covering all of them, but even then I won't be able to come with a most reduced expression because of this fact that we are choosing more overlaps between terms. If you look at the last one, our overlap is 3, right? This group of 0, 1, 4, 5 is overlapping with 5, 13 and 0, 2. That is 2 overlap, and group of 15, 11, 11, 10 are overlapping 1. So there are 3 overlap altogether in this group selection. Whereas previous both of these has only 1 overlap, right? Right here at between 0, 1, 4, 5 and 0, 2. The latter one has an where is this? Latter one has overlap between group of 0, 1, 4, 5 and 5, 13. There is 1 overlap. So both of these has 1 overlap, but the other selection had more than 1 overlap, and which actually result into more term in my reduced expression. Though it seems like from the visually, it seems like it's okay. We can, well, group it. They're covering all of them, but it still gives you a non-reduced expression. So be careful of this type of situation. Now another use of the term don't care. Let me first explain what the don't care is. A don't care term is those minterms which are not going to be appear in the lifetime of my function. By the way, this is little bit different than what a mathematical concept is, because mathematical concept says if it is a function of w x y z in a function, if I define my function as 137 11 15, then its inverse function would be rest of the minterm, right? Summation of rest of the minterm. But in digital circuit design, that world specifically, we have a powerful notion of don't care. Think this Boolean function, why we are optimizing and doing all this stuff. We are trying to make a digital circuit to solve a real life problem, right? To compute some real life quantity. In that problem, it might happen that by the specification of the problem itself, it might happen that some of the combination of these Boolean values of this related Boolean variables, some of the combination are guaranteed not to occur during the lifetime of that digital circuit. That means from the Boolean function perspective, those Boolean combination are not going to occur. Okay, and we may call it a don't term and create those don't care term as a form of d and then min terms those things. So what essentially this means, the digital circuit that solving certain problem which came up with some expression SOP, and it's also saying that during the lifetime of operation of that digital circuit, the min term like binary values related to those min terms 0, 2 and 5 will not occur. This means a combination of 0, 0, 0, 0 of wxyz variable is not going to occur during the operation. 0, 0, 1, 0 is not going to occur during the operation, and 0, 1, 0, 1 is not going to occur during the operation. So we call them a min term, don't care term. And for the don't care term, we place x in the box. So this is different from what math used to do. Like I'm not sure if math has don't care. It should not have theoretically to deal with don't care. This is specifically special consideration in digital circuit design domain. So we make a don't care term and we treat them as one if and only if it helps me to create a bigger group. We do not need to treat them as one, but we can or we may treat them as one if and only if it helps me to make the group bigger. Let's see. Originally, let's say without don't care consideration, we'll have this group, right? Which function is yz or w bar x bar z. Now, with this don't care consideration, it seems like I can make a bigger group like this, which includes two don't care term, which makes yz w bar x bar, or we can make this group 1, 3, 5, 7 as a bigger group, which will give me yz or w bar z. Right? So we can pick up any such group, but we don't want to pick up like as if we need to cover this 0 and 2 term, because we don't need to. So we are thinking x as a 1 only if it helps us to make the group bigger. So in the first case, it made a bigger group out of 1 and 3, that group, a bigger group 0, 1, 3, 2, and the latter one out of this group 1, 3, it make a bigger group of 1, 3, 5, 7, so we include them as needed. Now putting all this concept together, just point by point, right? Grouping of the neighboring terms, 1 in the K-map boxes, group of 1, 4, 2, 4, 8, power of 2. All possible groups are implicants in terms they are determined determine optimized function expression, and we do not in terms the okay. So this sentence is saying in terms determine optimized function expression. We usually do not care about this one, of course, because we are only caring about the essential prime implicants, right? So we start with the implicants, but we possibly sometimes we do not even care to put together all the possible implicants carefully, right? We sometimes we just make a shortcut and just straight go towards the essential prime implicant grouping and just make the optimization done. That's what it's meant by this sentence. Now, all the maximal groups which cannot be extended further into bigger groups are primary implicants, right? So all possible groups are implicants. So we can start with a group 1 and then make it group 2, then make a group 3, group of 4 and group of 8. So we only care about groups which represents prime implicants, right? All the possible implicant groups are not, usually don't care about that. Now for the prime implicant, when you are determining the prime implicant from a K-map, first do not bother about overlapping at this point. May overlap each other. To identify maximal group, we are allowed to include X in our group, but if and only if it is helping us to make a bigger group. Now it is not necessary to include all the X appearing in the K-map. So you can, some X's can be left out. Use those X only, it helps you to make a bigger group. Now the next point, for K-map with X, prime implicant should have at least one in that group. That is, like, you do not make a group with all X's. It doesn't make sense, basically. Make a group of all X, right? So don't make a group of all X. You have to have at least one inside a group. Like in a group of 4, there can be one and rest of 3 are X, fine. But all of them are X is not fine. It's not needed. It doesn't make any sense. Now, then you examine every primary implicant group that you have identified and answer yourself, does this group contains at least one which is not covered by any other group? If your answer is yes, it is an essential prime implicant. If this answer is no, it is not essential prime implicant. Now if you encounter a situation of selecting one prime implicant groups as essential prime implicant, which will make another prime implicant group non-essential and vice versa, pick up one of the group with maximum 1. Okay, let's say we have 2 possible groupings that I can pick up as my essential prime implicant, which will make other group non-essential prime implicant, and one group has 2x and other group has 1x. So we pick up the group with 1x. Okay. Now, if you encounter a situation, there can be multiple combination of essential prime implicant to make reduction equation. Choose those combination of the prime implicants to the essential prime implicant with a least overlap. Okay, that's the third essential consideration. So we start with implicant, not important. Then we identify all such prime implicants. Inside prime implicants, we are allowed to include X if it helps us to make a bigger group, but we do not make a group with all X's. Then for every primary prime implicant group, you ask yourself if this group is containing at least 1 or not. If your answer is yes, it's essential prime implicant. If its answer is no, it's a non-essential prime implicant. So you need to check if this group contains at least one which is not covered by any other groups. Then if you are encountering a situation where selecting one prime implicant group makes another prime implicant non-essential, then you pick up the group which has a maximum 1 or minimum number of X. If you encounter a situation that you can possibly have several combination of prime implicant to promote it as an essential prime implicant, then choose the combination with the least overlap possible. Okay. So that's all for this Boolean Algebra 2, this lecture. If you have any question, please send me an email or ask me in the class.